Hi, everybody. I'm just going to give it a few seconds because people are joining the session now before we start, just so we can all get settled. Right, okay. I'm actually going to start now because we're up to just over 100 people for the session. Welcome, everybody, to Quantum.Tech International Virtual Day. This morning's session is a keynote address by JP Morgan's role in driving quantum innovation. I'd like to introduce Marco Pistoia. He's a managing director, distinguished engineer, and head of research and engineering and head of quantum technology at JP Morgan Chase & Co. Handing over to you, Marco.
Thank you very much. I really appreciate it. And I am really honored to be here today. So thanks a lot for inviting me to give this keynote presentation at Quantum.Tech. And I will cover the importance of quantum computing for financial institutions. First, I would like to go over the fundamental concepts of quantum computing before delving into the importance of quantum for finance. So why are we even working on quantum computers? The reason is that computers in general were introduced like in the past century. The main goal for introducing computers was to actually simulate the nature around us. But the computers we are familiar with, which we call the classical computers, based on bits, zeros and ones, do not really lend themselves to simulate the nature around us, because the nature is not a binary. This is exactly what Richard Feynman, a Nobel Prize, a Nobel laureate said, like nature is not classical, so we cannot use classical computers to simulate the nature around us. Since the nature is quantum, so we need to actually have computers that can model these particular characteristics of quantum mechanics. And the first of such characteristics is superposition. So we're all familiar with the fact that in classical computing, the fundamental unit of information is a bit, which can only take two values, either 0 or 1. But in quantum computing, this is no longer the case, because the fundamental unit of information is actually a qubit or a quantum bit. And a qubit can be 0, it can be 1, but it can be any combination of 0 and 1. So let's look at these two formulas here, which you see the qubit indicated with the Greek letter psi. So a qubit is in fact, can be seen as a vector with two coordinates, C0 and C1, that are complex numbers. It is required that the sum of the norms squared, C0 squared plus the norm of C1 squared, has to be 1. And so basically what happens is that the qubit can also be interpreted as a linear combination, as you can see here, C0 multiplied by vector 0 plus C1 multiplied by vector 1. And this is actually an element of the vector space C2. So for example, let's take as an example a situation in which C0 is 1 and C1 is 0. In that case, we get the classical bit 0. If C0 is 0 and C1 is 1, we get the classical bit 1. But C0 and C1 don't have to be 0 and 1s. They can be complex numbers in general. So this shows that a qubit in superposition of 0 and 1, it can take any value. And the two coefficients C0 and C1 are known as complex amplitudes. And given that the sum of the norms squared is 1, C0 squared and C1 squared can be interpreted as probabilities. So when we measure a qubit, the qubit collapses to a quantum, to a regular bit. It becomes 0 or 1. But the probability for it to be 0 or 1 is given by the complex amplitudes. Actually, it's given by the square of the norm of the complex amplitudes. So the second principle of quantum mechanics that is at the foundation of quantum computing is called entanglement. And this is something that was discovered in the past century at the beginning by Einstein and other scientists. The interesting phenomenon of entanglement is that particles can be entangled with each other. So this means that the quantum state of each particle cannot be described independently of the state of the other particles in the same entanglement group, which means that if the property of one such particle changes, the other particles in the entanglement group will see the same property changing instantly, no matter how far away in space these properties are. So how can we describe such a complicated concept using classical computing? We definitely needed quantum computers, something that reflects this particular property as well. And an interesting consequence of this is that every time you add a new qubit to a quantum computer, its computational power doubles. So this means that the computational power of a quantum computer actually grows exponentially with the number of qubits. And this is a property that we don't see in classical computers. And this property has incredible consequences. For example, let's take an example that might not be really immediately linked to finance, but I think it gives the idea of the computational power of quantum computers. So quantum computers lend themselves to many different industries. And one of these is, for example, the pharmaceutical field or the new materials and energy, in which it's crucial to be able to simulate molecules using a computer. Before a new molecule can be assembled, it's necessary to make some computations and understand if the different atoms that chemists are putting together are going to have a sufficiently strong bond to make the molecule stable. And also from a pharmaceutical point of view, it's necessary to ensure that these molecules can actually bond to, say, a protein, a virus, to the receptors of a virus, for example, in order to make the virus unable to cause damage in the body. So precision is fundamental here because we're dealing with drugs in chemistry. And so it's necessary to have these simulations really precise. Now, we know how to simulate water, for example, using a classical computer, because as you can see, it only takes 10 to the power of 4 classical bits, which is 10,000 bits. It's nothing for a classical computer. But this type of computations these computations become immediately prohibitive as the molecule grows in complexity, because this complexity grows exponentially. So as we start looking at caffeine, we see that to simulate the molecule of caffeine, we need 10 to the power of 48 classical bits. Now, in comparison, the number of atoms on the Earth is 10 to the power of 49. So this means that there will never be a classical computer capable of simulating caffeine, which is not even a complicated molecule, and it's not even interesting from a pharmaceutical point of view. So you can imagine, as we make these molecules more complex, classical computers cannot really help unless we resort to approximations. And approximations are not ideal when dealing with with drugs. That's where side effects can come into play and so on. So let's look back at caffeine one more time. We just said 10 to the power of 48 classical bits. It's a gigantic number. But from a quantum computing perspective, it only takes 160 qubits. And we're not that far away from this milestone, from being able to have computers with 160 qubits that are also good quality qubits. So that actually, I think this I love presenting this slide because I think it gives the idea of how far quantum computing can go and help us, not only in finance, but in every aspect of our life. It can help society in many different ways. It can also help us reduce carbon emissions, because we can actually use quantum computing in new materials, in the new materials industry, to devise new fuels or new batteries that are more durable, they can be recharged faster. So eventually move away from fossil fuels and other forms of energy that are highly polluting. But let me actually tell you another example that might be, even though the figure doesn't show this, but please bear with me, this actually is closer to finance. So interestingly, there are 10 factorial possible ways to sit 10 people around a table. 10 factorial is 3,628,800. So it's a very large number, not impossible at all for a classical computer to handle, but still it's surprisingly high to think about how many different ways you can sit 10 people around your dinner table. And of course, because it's factorial, it grows so fast, and it gets out of hand really fast. So if you think about a portfolio optimization in which a financial institution has to compute an optimization problem, has to solve an optimization problem with, say, 1,000 assets, the complexity is prohibitive for a classical computer. But even if you look at logistic and transportation companies, they have to do, say, hundreds of deliveries every day. What is the optimal route for those deliveries? Taking into account the constraints such as traffic, length of the path, tolls, weather, all these things have to be taken into account. And again, the optimal route can be computed efficiently and accurately with a quantum computer of the future, but not, even though not now, but a classical computer will never be able to get the exact answer to many of these questions. So that's why we are interested in quantum computing for finance. Right now, we're not capable with today's quantum computers to really solve problems that are the problems that financial institutions have to face every day. The quantum computers are not sufficiently powerful or sufficiently accurate. In the last century, all the work in quantum computing was at a scientific level, to understand how to devise a quantum computer and to understand what type of algorithms could be designed and implemented for quantum computers. But now that quantum computers have finally become available, even though at a smaller scale, it's time to realize that quantum computing is a reality. And in this decade, we will actually see quantum advantage. Quantum advantage is actually a milestone in the history of quantum computing that we expect to come in a few years. And in quantum advantage, quantum computers will be able to surpass classical computers and do better than classical computers. So classical computers at that stage will still be useful. They can still solve the same problems, but quantum can do it faster and more accurately. There is yet another milestone called quantum supremacy, which will come later on, maybe towards the end of this decade. With quantum supremacy, which has already been proven theoretically and practically by Google in 2019 with a very famous Nature paper. In quantum supremacy, we will see applications that can be solved by a quantum computer, but not by a classical computer in any reasonable amount of time. So that will be like a completely different type of milestone. So what can we do now given that the quantum computers are available, but not yet scalable enough to solve our daily problems, our daily challenges. There is an important thing that we need to do. It is to become quantum ready, which means we need to actually use the resources that we have to build assets, to build a portfolio of quantum algorithms and applications for the different domains in which we are involved. For example, in finance, we are building algorithms to solve portfolio optimization, option pricing, risk analysis, and a lot of problems in the realm of machine learning. The reason why we need to do this now is because if we are not ready by the time of quantum advantage, we will be in a position of disadvantage with respect to other companies. So we cannot be caught unprepared when the time comes. This is a crucial time, actually, for many corporations and also for academic institutions, government research institutions, for everyone to actually start building an infrastructure for quantum computing. I wanted to give credit to McKinsey and company for this diagram on the right. There is an interesting survey, an interesting report that McKinsey created, showing the disruptive effects of quantum computing to the industry. And it's interesting to see that finance is actually expected to be the first industry sector to benefit from quantum computing, not only in the medium and long term, but even in the near term. And the reason why this is the case, as opposed to the other industry sectors, is that the finance has a lot of use cases. Like pretty much a lot of the things that we do in finance every day have extremely high complexity. And so the financial use cases lend themselves to the exponential computational power of quantum computers. Now, it could be said the same thing also for pharmaceutical and medical products, but it is also true that in finance, we need quick answers right away, even with some approximation. So as of today, we're already approximating our solutions. Otherwise, we wouldn't be able to solve our problems like portfolio optimization, option pricing, risk analysis. There is already an approximation happening today using classical computers because these problems have high complexity. And so the only way we can solve them efficiently is by using approximations. In finance, the approximations are already taken into account. So if a quantum computer comes along with the quantum advantage tag on it, we will be able to reduce the number of approximations. And so finance will benefit right away from quantum. This cannot be said, unfortunately, for pharmaceutical and medical products. For example, those products require extreme precision. And so maybe we expect the pharmaceutical and medical products to benefit from quantum later on, but definitely there is an advantage for every of these industry sectors. So I wanted to actually let you know about the different use cases in finance. This is what we're working on at JP Morgan Chase. And many of the algorithms that you see on the right have already been implemented. So we have already identified the right algorithms for these use cases, which have been grouped into three categories, like Monte Carlo simulations, optimization, and machine learning. So at this point, our work consists of either devising new algorithms or improving the existing algorithms and trying to making sure that these algorithms can already become suitable even for the near-term quantum computers. For those who are not familiar with these terms that I have used, like exponential complexity or quadratic speed up or polynomial complexity, I wanted to show this diagram here, which shows how fast the complexity grows when it is exponential. You can see the red curve, it like blows up immediately, even with very small data sets. With quadratic speedup, we still have exponential speedup, with the only advantage that the exponent has been divided by 2. And then with exponential complexity, in this case it's quadratic, you can see that the curve, of course, grows, but in a much slower fashion. So at JP Morgan Chase, we have already created a platform for quantum computing, which we named OmniQ, that has all the layers included. We have the domains and applications. We have algorithms. We also have classical algorithms that we use for comparison to produce reference values. And we have a level of circuits that is actually hardware agnostic. We use Ticket from Cambridge Quantum Computing to make sure that we can pivot from one hardware provider to another efficiently, so that we can be ready for quantum advantage when the time comes on any computer available. And our platform has been organized according to the strictest principles of software engineering, such as modularity, extensibility, and you can see here, like algorithms can be partitioned into components. So these components can actually be reusable across different algorithms. And this allows us to do research in a very directed way. So if we can actually focus just on one component that we want to improve. But I would like to finally mention one important concept as well. So quantum computing is actually a great technology. I am very passionate about it. And that's why we're here today, because we believe in this technology, we are passionate about it. And quantum will be able eventually to solve a lot of problems. But unfortunately, it also solves problems that, frankly, we didn't want it to be able to solve. And one of these is the ability to factor large numbers into prime factors, which is a problem at the foundation of public key cryptography. So it has been estimated mathematically that 2048-bit RSA key can be broken in only 8 hours with a quantum computer expected to be available maybe in about 10 years from now, around the time. This result was published by Google and Sweden's Royal Institute of Technology. On the other hand, the classical computers will require about a quadrillion years in order to be able to achieve the same result. So you can compare 8 hours versus quadrillion years. This means that attackers will be able to decrypt private communication, will be able to infer the private key of individuals and corporations, impersonate entities, break cryptocurrency and blockchain technology. It's really, it's going to be a total disaster. But there are solutions that are being taken at this point. One is called the PostQuantum Cryptography. It is algorithmic based. And so basically what happens is companies are, cryptographers are currently devising new cryptographic algorithms that are quantum resistant to the extent that nobody has yet found out how to use quantum to break them. And then there is another technology we are working on at JP Morgan Chase. It's called the quantum key distribution, which is based on principles of quantum mechanics, the principles of measurement and no cloning. And so it's actually unconditional. It has unconditional security as proven by John Prescott and Peter Shor. So it's a mature technology already for short distance, but not for long distance networks. So for short distances, less than 100 kilometers, which are suitable for metro areas, QKD is already available. For long distance, we need a technology to be in place, and we're doing research on that technology. It's called the quantum repeaters, or alternatively, we can use satellite quantum communication. So this is exactly what we're working on at JP Morgan Chase. So to summarize, quantum algorithms and applications for finance, and we're looking into securing our platform using post-quantum cryptography and quantum key distribution. I would like to finally say that even though quantum computers will be able eventually to break cryptography, years from now, maybe 10 years, maybe 12 years, who knows? That doesn't mean that we have a lot of time. As a matter of fact, attackers are already known to be taking snapshots of private data with the intent of decrypting it later. So they take the snapshots now. They cannot decrypt it because the computers are not powerful enough yet. However, they will decrypt the data later, and sure enough, the data will still be valuable and sensitive, even like 10, 12, 15 years from now. So this is something, this transition to quantum resistant technologies has to be implemented now as soon as possible. And this concludes my presentation, and I have a URL here. I'm the head of the Future Lab for Applied Research and Engineering at JP Morgan Chase. So if you Google us, you will be able to find out more about what we're doing. And I would like to say we're also hiring. So please let us know if you have interest in joining us. Thank you very much. And at this point, I'm ready to answer some questions.
Okay, thank you very much, Marco. That was wonderful. There are quite a few questions. So rather than me type them in the chat, I'm actually going to ask you. I think it might be a bit quicker for you. I've got a question from Pathikrik Mukherjee that has said, at the heart of quantum computing is designing quantum circuits. For an example, Grover's algorithm. To prove Grover's algorithm, we need a quantum circuit. The question is, when we try to simulate a system such as a molecular system, as you mentioned, how do we start designing the quantum circuit to make sure you finally arrived at the desired outcome? And how precisely do we have to determine that out of many different quantum circuits, which one would be the most successful?
That's a very good question. This is actually good because we work at the level of algorithms and applications, but algorithms are eventually compiled into circuits. To answer this question, what people are doing now, including ourselves, is of course trying to make the circuits as efficient as possible, which means the circuits should be shallow enough. So with like if you look at a circuit, it looks like a pentagram in which the rows are qubits, and then the operations on the qubits are called gates. So it's necessary to make, of course, the circuit small enough to match the number of qubits of the quantum computer that we're targeting. We cannot have on the circuit more qubits than what are physically available. And also it's necessary to make the circuit shallow enough so that it can be executed within the coherence time of the quantum computer that we're targeting. So these are called, of course, near-term quantum computers. In the future, we expect computers to be able to deal with deeper circuits. But for now, I think to answer your question, we should make the circuits small enough so there are techniques that can be done to optimize circuits. So there are circuit optimizers, and also we can make the problem small in the sense that, for example, as you mentioned, a pharmaceutical company, we're not at the point of being able to simulate caffeine, as I mentioned before, but we can simulate water. Now, it's totally useless to simulate water for a pharmaceutical company because water is not of it doesn't have any interest in pharma. And a classical computer can do the same thing. However, by building an algorithm that can simulate water now, we can then extend that algorithm as the computers become more powerful. So we already have an algorithm that simulates molecules, water for now, and as time goes by, it can be a more complicated molecule, it can become caffeine, and it can become a real drug. So I think we need to be able to build algorithms now and adapt them over time.
Okay, I have another question for you. We'll see how many we can get through from Michael Kurek. He says, what will be the killer app for quantum for finance, Monte Carlo, optimization, QML, and which one could come first?
This is actually another very good question. So So for optimization, we have very good algorithms that, and new algorithms are being devised all the time. So we have variational algorithms that lend themselves to near-term quantum computers. Unfortunately, variational algorithms have unproven speed up. So, but still, the advantage is that they can be used on today's quantum computers. Then we have the ability to use search-based optimization, like a Grover-based optimization, in which case the speed up is quadratic. And if the problem lends itself to, like an optimization problem can be cast into a system of linear equations, and under certain conditions, so in general, a system of linear equations can be solved using HHL. Under certain conditions, HHL can even have exponential speed up. So the idea would be to find out how to make this happen. Now, for option pricing and risk analysis, algorithms have been identified. They use amplitude estimation, in which case the speed up is quadratic. And then there is the whole realm of machine learning. We think that maybe Monte Carlo simulations will actually hit first. Potentially optimization if we find a way to exploit the HHL algorithm because of its very strong advantage. And machine learning can also be an area where we can see quantum advantage coming first, depending on the type of problem and the amount of approximation that we can deal with.
Great, thank you. There was lots more questions, but I know we're running out of time. Thank you everybody for tuning in. We hope you enjoyed the rest of the day, and thank you very much, Marco. That was a fascinating presentation.
Thank you very much.
Thank you.
It was my pleasure. Bye-bye.
Thank you. Bye-bye.